Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're continuing, oddly enough, the chain rule. Even though this says derivatives of exponential functions, theorem and proof, and examples, there should be commas there. It is actually nested within the chain rule. See what I did there? Because you need the chain rule to prove this theorem involving exponential functions. We already know, by the way, that the derivative with respect to x of e to the x is e to the x. So that is not the exponential function that I'm worried about. I want to prove something about the derivative with respect to x of any base to the x, where the base obviously is positive and not equal to 1, because then in those cases it's if the base is not positive, or if it is equal to 1, it's not an exponential function by definition. So here's the theorem, very short. The derivative of y equals b to the x is just b to the x times the natural log of b. I want to give you a bit of fair warning here. The proof, it's not hard, but it involves something from the future. Yeah, it does involve something from our future. Actually, it involves something called logarithmic differentiation, but that's okay. It's pretty easy to understand within this proof, so I'm still going to do it because it's a really neat way to differentiate. You know what? Actually, I just paused the video to try out a different style of proof, and I think it works, so I'm going to do it. So let's go ahead and do this. The derivative with respect to x of b to the x is defined to be the limit as h approaches 0 of b raised to the x plus h minus b raised to the x all over h. That's not a big deal. Then we can say this is the limit as h approaches 0. We can factor off a b to the x off of both these terms. So it'd be b to the h minus 1 all over h. And of course that x does not rely upon h, so I'll scoot it outside. So this is b to the x times the limit as h approaches 0, b to the h minus 1 over h. That's not too terrible. Now I'm going to use a little fact that if you have b to the h, that's the same thing as e to the natural log of b to the h power. That's as long as the base is positive, by the way. So natural log, e to the natural log of b to the h power, those are the same thing. You should know that because e and natural log are inverses of each other. That will return b to the h. So let's go ahead and write that in here. This is where my proof is slightly different than what I thought I was going to do, but I just decided to try this, and I think it works beautifully. This is going to be e to the natural log of b to the h minus 1 all over h. And of course, you could use properties of exponents to pull that h out front if you want, and I want, so I will. That's b to the x times the limit as h goes to 0 of e to the h times the natural log of b minus 1 all over h. And here's where I kind of thought, maybe this proof won't work, until I realized it will. We're going to let k equal h times the natural log of b. B is a constant, it's positive, it's not 1. Okay, so if it's a positive, not 1 constant, then as h goes to 0, k will go to 0. If this was not constant, if the natural log of b wasn't constant, then I couldn't make that claim, but I totally can now. The limit as h goes to 0 of h times natural log of b will be 0. So therefore, the limit as h goes to 0 causes k to go to 0. Same thing, the limit as k goes to 0 causes h to go to 0. So we have that, which tells me, by the way, that if I want to replace h, I could. It's k over the natural log of b. I'm going to do that. This will be b to the x times the limit as h is tending to 0. E raised to the h times natural log of b is now called e to the k. Oh, by the way, I'm going to switch this out for k going to 0. Minus 1 over, instead of h, I'm rewriting as k over the natural log of b. So let's see what we get here. This is b to the x. The natural log of b swoops up to the top, and I can move it outside, in fact, because it's a constant, times the limit as k approaches 0 of e to the k minus 1 over k. Now, if you've been watching my video series, then this might be familiar to you. E is the only exponential base whose limit as k goes to 0 of e to the k minus 1 over k is equal to 1. So it's the only exponential base with that property. So that's a reminder. And I wrote it off to the side. So there we go. This ends up being just b to the x times the natural log of b. I didn't have to use anything from the future. So this tells me the derivative of an exponential function, base b, raised to the x power, is equal to, through a bunch of equal signs, b to the x natural log of b, QED. Let's go ahead and use that. Honestly, this theorem is so short, and I normally would probably reserve another video for examples of taking derivatives of exponentials, but you only need one. That's all you really need. So let's go ahead and do it. Find the derivative of y, which is equal to 2 raised to the secant of pi x. Watch how I do this. I'm going to write this down. Y is equal to, the outer function is in black, 2 raised to a power. Okay. The power is my inner function, secant of. However, the interior of the secant is actually yet another function. It's a pi x. So outer function 2 raised to a power of, that is. Next innermost function is secant. And the next innermost function is pi x. All right, so let's go ahead and do this. I don't know why that's doing that. So y prime is equal to, the derivative of 2 to a power is 2 to that very same power times the natural log of 2. Again, that's from this theorem right here. The derivative of 2 to the x is 2 to the x times natural log of 2. Of course, we're not dealing with x here. We're dealing with the chain rule, but still, same idea. But now that I'm done with the derivative of that base function, 2 to the power, I will concentrate on taking the derivative of the secant. So I'll attach to that the derivative of the secant. Derivative of the secant is the secant times the tangent. And of course, the arguments of these are going to be the arguments of the secant function there, so pi x. Now I can erase that outer function and take the derivative of the innermost function. The derivative of pi times x is just pi. And there we go, we're done. Very good example. You do have to realize that, let me erase this, that when you're working with the chain rule, just remember you're taking the derivative of the outermost function, erasing that, taking the derivative, attaching to that the derivative of the inner function, erase that, then take the derivative of the inner function to that. All attached by links called multiplication. And I thought that was the last example, but I actually have one more. So suppose that f is differentiable on the real numbers, or over the real numbers, if you will, and let capital F of x equal f of little e of x, or e of x, e to the x, sorry, and g of x be e to the f of x. Find expressions for capital F prime and capital G prime. Now that's actually kind of easier than the rest. Capital F, remember, is little f of e to the x. And we're told little f is differentiable. So we're okay. It's differentiable for all reals. So let's see, capital F prime. Derivative of the outer function. So little f prime of e to the x. I'll erase that. and then times the derivative of the inner function, which is just e to the x. That's it, folks. Like, that's literally that quick. G of x. Well, that is e to the f of x. So g prime of x is equal to, the outer function here is e to a power. The derivative of e to a power is e raised to that power, actually. So we've taken that derivative times the derivative of the power itself, and you're done. Before we leave this lecture, I do want to mention something about the theorem that we just introduced ourselves to, this guy right here. Notice that we introduced ourselves to this theorem well after we learned that the derivative of e to the x is e to the x. Turns out this theorem works with that. The derivative with respect to x of e to the x, according to this theorem, should be e to the x natural log of e. But what's the natural log of e? Why, you're absolutely correct. It's the number 1. So it does check out. I just wanted to make sure that you knew that that theorem for the derivative of an exponential function holds for all exponential functions, not all except for e to the x. It holds for every single one of them.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.